video we'll use materials from this so-called the user, and the one who created this video is all over here. Alright, as seen in the screen over here. Alright. And for beam in bending, you have a neutral axis that is in between this thing. Alright. And at the top you have a compression when you bend, and at the bottom you have a tension, stretching. Alright. And we're gonna use this concept and see how do we build on things. Highly suggest that you watch all this video if you are free. Let's focus on in this video. Let's focus on a few videos now. Alright, so therefore let's just start off with this one first.
When a beam made of an elastic material is bent, both the stress and strain increase with distance y from the neutral axis. At a certain point, the material cannot carry any more stress. The material reaches what is called its yield stress, denoted as sigma yp. If the beam is bent more, permanent deformation occurs. As the beam is bent, some of the extreme fibers yield. That is, they reach and carry their yield stress. Those fibers that are in tension at their yield stress will be permanently stretched, while those in compression will be permanently shortened. Those fibers that have not reached yield stress are still elastic and are governed by Hooke's law. In summary, stress is linear with respect to y in its elastic range, but in the plastic range does not exceed the yield stress. Strain, on the other hand, remains linear with respect to y throughout the depth of the beam. Another way of looking at the relationship between stress and strain in the elastic plastic case is to use the stress-strain curve to determine the stress at each point. If the radius of curvature is known, then the strain can be found at any point using the equation epsilon equals minus y over rho. The fiber shown in green is in its elastic range. The stress at this strain value can be read off the stress-strain graph. For another point further from the neutral axis, the strain is above the yield strain, epsilon yp, and the stress is sigma yp. By repeating this process, the stress at all points across the depth of the beam can be found.
Alright, and therefore as you can see, I'll just crop a few stuff, hold on a while. So for a straight beam in this case, as you can see over here, you have a certain neutral axis, NA, okay? And that if it's a straight line like this, alright, if it's over here, if there's no bending, your y is in fact just on this side, alright? And as you go by, as you start to bend, alright, this thing will start to go and turn into this direction, correct? And this can be plotted by the strain is equals to your minus your y, which is your neutral, the distance from your neutral axis. Maybe you're talking about this piece is the distance from the neutral axis divided by your radius. Alright, when you bend, you have a certain radius. Alright, so there is a certain radius over here. Alright, so this so-called the rho over here is your radius, your curvature radius. Or in other words, still the same thing, my equals to er, or maybe this one. Alright, so yeah, nearly there, alright, somewhere there. And therefore we also know, and in addition, we also know that when you bend this particular beam over here, alright, at this point of time, this particular point, it's actually so-called starts to yield already. Alright, at this tip over here, it starts to yield. However, because your stress is all acting, I think the stress is over here because this is talking about the compressive one and the tensile one. Alright, so the stress mainly focus on here. Alright, focus on here, and at this point of time, these stresses actually experience more stresses than others. So this point over here and this point over here actually experience less stress. Alright, less stress than the middle part. Alright, better let you know and feel how this so-called this curve is coming and why is it elastic over here and the rest are non-elastic. Alright, so in this zone we can call this the elastic plastic alright zone. Alright, so I'll show you the next video of regarding this. Alright, hold on a while. So let's continue with this video and see how it goes.
The stress distribution in a beam that carries a partially plastic moment looks like this. The arrows show stress values at various locations on the cross-sectional area. To find the total moment carried by the beam, we add up the contributions of stress from each area of the cross-section using the moment equation. In this case, it is convenient to break the integral into three pieces, namely the top plastic region, the elastic region, and the bottom plastic region. In the elastic region, where stress equals E times strain, or minus E times Y over rho, the moment contributed by this area.
Okay, let's just pause the video and go back to this particular picture over here. Alright, and let's crop this out. Here you have a bean. I actually slice it into three parts. Okay, I slice it into three parts, and if I were to bend it, this top part here gonna experience a somewhat compressive one. Alright, while the bottom one will experience a tensile one. Alright, so the forces actually somewhat distributed over here, the middle part. Right, while the middle one, because will have a lesser, this middle part will have lesser so-called stresses compared to this top part, right? Because all the stresses are all going onto this point. Alright, it's all going onto this point, the top part. So therefore, we can see that if you were to zoom into this portion over here, maybe wait this portion over here, then it's something like this. So this is the top part that I said earlier. Alright, this is the top part. So this top part experience somewhat the non-linear stress, or we call this the plastic stresses, because it already starts to yield already. So all, if you were to take a look, if it's how do I say? For example, if I were to put this beam, let's say we have a straight beam now, alright, I were to draw a line over here, or maybe you apply a layer of water or water-colored stuff. As you bend, alright, you can see that this particular thing, alright, that the line itself starts to go like this. Alright, as it goes on. Alright, so you can see that the flow of the plastic actually goes in this direction. It's 3D, then it's this case, right? And then if you were to bend, some of the material may actually flow out. Alright, may actually be something like this, may actually crumple. Alright, and this flowing somewhat represents the flowing of this part. Alright, so the surface of it starts to flow. Alright, so at first it was like this. Alright, it was like this. Then when you start to bend, starting to bend now, okay, when you start to so-called bend it, this thing will start to go in this manner. Alright, the arrow over here, and this part will start to stretch. So far so good. And the next second layer, if you were to further pull it, alright, and when it reaches its yield strength, alright, maybe I should translate it over here, alright, it will start to somewhat like this. So this part here will actually flow in this manner, alright, so they actually crumple all this. That's why you see the shape became like this, alright, or maybe if you were to explicitly define, which is also shown over here, as you can see, all this part over here is a bit so-called push. Alright, it's going in this manner, right? I shouldn't have drawn this thing over here. I actually draw it wrongly. For the tensile part, it should be something like this. Okay, also have some form. Okay, which is somewhat going in this direction. Alright, trying to so the bottom plate will be something like that. Will be pull or whatever, will be stretch. So as you can see, it's shown over on the side also. So the tension is actually being pulled. On the middle portion over here, experience lesser stress because it's further away from the stress point over here, or on the tensile area. This is on the compressive one because it's compressed, and then the stress point for the tensile is this point. So the middle one is actually experiencing lesser compressive or lesser yield stress. Alright. Likewise, if you were to compare this primary point and this point over here, which is the top point, this top point also experiences lesser stress than this point over here, and therefore it may not yield such faster speed. So maybe it may have this type of curve also, something like this, I would say. So therefore we can see some form of a trend. Or maybe I should show you the video. Hold on. And therefore let's watch this one.
As the moment acting on a beam increases, the stress distribution changes accordingly. We give names to some of these moments. The fully elastic moment, denoted as MFE, is the maximum moment that can be applied to a beam without any of its fibers yielding. This moment occurs when the fiber furthest from the neutral axis just reaches its yield stress. A moment that causes some fibers to yield is called a partially plastic moment, expressed as MPP. There are a range of these for any particular beam design. Finally, the moment that is strong enough to cause all fibers to yield is called the fully plastic moment and is written MFP.
Alright, and therefore this will actually talk about this page over here. So this page is when, maybe this one is of elastic region, and this is the plastic elastic region where we have discussed just now. Alright, from this thing over here. Alright, so if we go into this view, what you can see is something like this. Alright, so this shaded part are all the plastic region, these are all the elastic region. Alright, and therefore if you talk about fully plastic, where it reaches this point, then this means that it's fully yield, or it's fully yield. For beam, in this case, maybe a full beam, maybe you have a beam over here. Different point has a different curvature. Alright, and maybe at this point you have a different curvature, at this point you have a different curvature because of the stress distribution. Alright, if you were to bend it, this one will compress. This one will compress, this one will also call pull it, and therefore sorry, my pen is so at this point over here, alright, it may start to yield a little bit. So this is somewhat the graph. Am I drawing the correct graph? Yeah, I keep having the problem drawing the correct graph. Something like that, okay? So at this point is somewhat this plastic elastic region. But however, at the tip over here, which experience a lesser stresses, will be elastic. Alright, we'll still have this shape over here. Alright, while this part over here will have some sort of this shape over here. Okay, and things like that. So these are the things that you need to really take a look on. This page, if I'm not wrong, I don't know whether am I correct, but if you have a beam over here in 2D view, right, if you were to bend it, alright, there will be a compressive over here, which is something like this, alright, and there will be also somewhat a tensile stress going in this direction. And therefore this is something talking about this whole chunk over here. I may be wrong. The thing now is that this one over here is a fully plastic. Alright, you should have this curve over here. Why are they drawing this curve? Alright, it should be something like this. Right? I don't know. So somewhat, I don't know how to explain this, but at least you get to see that the top one is being compressed, this bottom one over here, alright, is being stretched. So if you were to go into like this, something like that, where this one is your stuff over here, and as you were to continue to bend it upwards over here, alright, this thing will start to elongate, alright, things like that, okay, and soon when it becomes plastic, alright, then it will be something else, alright. If you have drawn properly, this one is like this when you start to bend a bit, and when you bend a lot, the portion over here will start to flow, alright, so the plastic flow will begin, but this linear part over here is still linear, okay, but up till a certain point where you continue to bend it, you can see that they actually become two pieces, alright, and things like that. Therefore, if you were to talk about the other directions, then it should be over here. Then it's talking about this thing and this thing over here. Alright, so to speak. Alright, so if you were to continue to do this, you plot out all the stuff over here. But if, let's say, if you apply this particular stress already and then you release, then the residual stress or the residual stress is over here. Alright, take a note that is being drawn with a similar shift, but this thing over here will be plotted over at this side, while this thing over here will be plotted over at this side, based on the switching of the stuff. I don't know how they switch, but it's just the switching of how we're going to look at things. Alright, this is to my best knowledge the understanding of the plastic bending of a beam. Alright, if you were to elastically bend it, you have this shape over here. If you were to go into this region, elastic plastic, you have this region, and if you were to fully plasticize it, then you have this thing over here. Alright, and soon it will break. Alright, and therefore this is it for our stuff. So in the next video we'll talk about other stuff. See you there.